automatic generation of grammar-agnostic visualization and infographics using large language models. So hopefully we're talking about GPT 3, 4, and things like that. Yeah, okay. So LIDA is a novel tool for generating grammar-agnostic visualization and infographics. LIDA comprises of 4 key modules: a summarizer, the goal explorer, a VIZGENERATOR, and an infographer. Victor will tell us what these things are and what they are doing. Okay, and it also provides a Python API and a hybrid user interface, direct manipulation, and multilingual natural language processing. Okay, and we are lucky to have Victor here today, who is a principal research software engineer at the Human AI Experiences team at Microsoft Research. His work focuses on generative AI, and he has interest in human-computer interaction, computational social science, and applied machine learning. So kind of cuts across different disciplines. His work has been published at conferences, core NLP conferences like ACL, EMNLP, AI, and so on. Okay, and has also earned multiple Best Paper awards and media attention, the Wall Street, the VentureBeat, and so on. Victor is also an IEEE senior member, a Google certified professional in data engineering and cloud architect, and a Google developer expert in machine learning. Victor holds a PhD from the City University of Hong Kong and a master's in information networking from the Carnegie Mellon University. So we're very fortunate to have you, Victor. You're very welcome. If you're ready, you can share your screen and start the talk now. Thank you.
Yes, so first of all, thank you to everyone for having me. It's great to be able to come back to university and sort of interact with folks. I'm hoping to talk for about 35, 40 minutes, and hopefully we'll have some time to sort of converse. My role at Microsoft Research is research software engineer on the Human AI Experiences team. So what that means is I spend a lot of time thinking of the engineering and practical aspects of using LLMs, and also thinking through like the user experience and applying all what we know about user behavior, cognitive psychology to sort of design user interfaces that actually end up in service of the user. In the last 2 years, some of the work the HAX team has done, so the Human AI Experiences team, has we started doing some work with Copilot. So how many of you are familiar with Copilot or use GitHub Copilot? If you can just do a raise hands of sorts. So GitHub Copilot, you know, we sort of talk about it as the original implementation, the first implementation of a really large language model deployed at scale to actually work in concert with users in solving a task. And the promise is a developer goes to their IDE, their development environment. They have this plugin installed there. And as they write their code, the system does a good job of inferring intent and then generating a large amount of code that actually solves the task that they're working on. To do this well, we need good metrics. So for example, some of the things my team has done has studied like how do offline metrics that we use to evaluate this model, how do they align with online metrics of value, things like acceptance rate and subjective like judgment of value, and can we create better metrics that sort of bridge this gap? More recently, we're looking at more interesting applied applications of LLMs, and one of them is using LLMs to sort of support users in the visualization authoring process. And so today, I'll be talking about LIDA, which is a tool for grammar-agnostic visualization and infographics generation. To break that down, grammar-agnostic just means that the system will generate visualizations using any programming language or visualization grammar. So for example, Matplotlib, Seaborn, VegaLite, D3, the proposed approach should be able to use LLMs to create visualizations in all of these spaces, all these grammar spaces. And then also, infographics means that we don't just get visualizations, we could get like stylized infographics that are conditioned on actual data. So the talk is going to have like 4 parts. The first is an overview motivation. Why are we interested in this topic? The second, will dive into the different components. So there are 4 high-level components, and so we'll sort of talk about how those are implemented. So the engineering design decisions behind that. Next, we'll briefly look at related work. So LIDA built in all of the advances and foundation models. It says foundation models for text and code, foundation models for image generation. It also is informed by a lot of literature on automatic visualization and also infographics generation. Then next, we'll look at how we might evaluate such a system. What are some of the challenges there? How do we know if the system works well? What are limitations? And then finally, we'll sort of look at lessons learned and then some potential future work, and then we'll have Q&A. Okay. Why might we want to spend a lot of time creating tools that sort of support the visualization authoring process? And in my opinion, I think the key value proposition here is that visualizations make data accessible, and they do this by reducing the cognitive load associated with sort of extracting insights from tabular data. So you might have a large data set with thousands or hundreds of thousands of millions of records, but really what you want is to answer a question. So you probably want to answer a question of what is the trend in my income? Is it going up or is it going down? And so visualization sort of summarize all of those insights and make it sort of easy to consume, and also helps you come up with good questions around the data. However, the process of creating visualization does require quite a bit of effort and skill. So in order to create a good visualization, you need to ask the right question, come up with good hypotheses. You need to figure out a way to represent those hypotheses as visual encodings. So for example, do I need to use a pie chart or bar chart? Or do I need to use an area chart or a Sankey diagram, these sort of decisions? And also, even before I select these encodings, is my data in the right format? Do I need to apply some transformations or some statistical operations? And then finally, once you figure out all of that, you need to figure out how do I sort of implement this thing in code? So do I write code for it, or do I use a direct manipulation tool like Excel or Power BI or Tableau that has some interfaces? And essentially, there's a bit of skill and effort to sort of do all of this. And the whole idea is that, like, we want to figure out ways to sort of, especially for novice users, help them come up with the right questions, help them figure out the right encodings and transformations, and then help them implement the visualizations. And the promise is that if we do this, we can truly create a better visualization authoring experience. And the impact can be twofold. So first of all, there's this whole swath of users who probably could not do all of these, and suddenly we have onboarded them, and now they can offer visualizations. It's a whole new capability for them. And then for those who are already skilled in that space, the goal is to reduce the time associated with this task. And so for me, I probably am comfortable writing Matplotlib code or Seaborn code for visualizations, but it's a much faster experience if I can describe my intent in natural language. And in about 10 seconds, I get a visualization that I can then customize. This would be like, maybe for me, like a 4 or 5 minute effort shortened down to about 10 seconds. And so one way we can do all of this is to explore automated visualization approaches. And so this whole area of research is not new. It's been a holy grail for the visualization community. And there's been a lot of work on being able to recommend visualizations to users just based on raw data. So I think even in Excel today, we have, I think, a tool called Analyze Data. And once you have your data in Excel, then it might recommend some visualization from some potential visualizations. However, most of the existing approaches do have limitations. And so, for example, some of the approaches, for example, in papers like Voyager, Draco, so these are papers from the visualization domain, they depend on handcrafted heuristics, so rules. For example, they might look at the fields, figure out, is this categorical, is this continuous? And based on these rules, they might map that to some visualization that might make sense for the data. The challenge is that these rules might not have good coverage, and also they might be tedious to update. On the other hand, we have some learning-based approaches that might seek to use machine learning approaches to recommend visualizations. Those also have limitations. So for example, they typically will depend on task-specific data and task-specific training pipelines. This can be very hard to sort of maintain. And in some cases, the user doesn't get fine-grained control over the output of the visualization. These methods do not learn from large-scale data. So this is just raw text and visualization examples and visualization best practices. And they do not cover output formats beyond images. So for example, they do not cover like the generation of infographics. So these are some of the limitations that LIDA tries to address. And some of the high-level approaches sort of adopted by LIDA is, number one, it seeks to leverage the language modeling and code writing capabilities of LLMs. And so what that means is that there's a lot of research that sort of shows that like LLMs like GPT 3.5, ChatGPT, and GPT-4, they excel at encoding broad world knowledge. And so, for example, they do very well on like standardized tests, the bar exam, some medical licensing exams, and actually visualization is not exempt. And so it turns out that these LLMs can encode visualization best practices. They also write code really well. And so if we sort of take these two capabilities, then we can use that to create something novel and valuable. For LIDA, we settle on code as the core representation of visualizations. And so it turns out that if you do that, then it's a good pathway to sort of leverage all of the broad world knowledge of LLMs and sort of apply that to visualizations. And I'll talk a bit more, give some examples of what that means. And then finally, we explore a multi-stage process. And so key modules that address specific tasks in the visualization authoring pipeline. So first of all, we have a set of modules that generate a visualization, which is code. And then we also have some modules that operate on this visualization for processes called VIZOps. And so if we have a visualization, can we refine it? Can we critique it? Can we come up with ways to improve it? And can we automatically repair it? So there's some examples of VIZOps. Okay, so before I go any further, I will try to do a live demo. So we all know how live demos go. They may or may not work, and we'll see how it goes. Let me share my screen, do a separate screen share. Can anyone confirm that they can see my screen?
Yeah, I can see it.
Great. So this is the interface for LIDA, and the flow sort of starts with selecting a data set. And so in this case, you might upload your own data set, but I have a few here. And so here it's just the S&P 500 CSV data set. And the first thing that happens is once you drag in your data set, LIDA attempts to use the summarizer module to come up with a compact natural language representation of the data. So this might take a while because it uses OpenAI on the background. And so for that, it might take a couple of seconds. But just for the purpose of demonstration, I have gone through this process a little earlier. And once the data summarizer is done, this is what the interface sort of shows. It generates a data structure that looks like this. And so, for example, here we have name, we have a description of the data set. We have a list of fields. For each of these fields, we have the title of the field, and then we have a set of properties. So like the atomic data type, mean and max value, a set of samples, the number of unique values, semantic type, and a description. So how is this constructed? It's constructed in a two-step process. So first of all, we have like a rule-based engine that parses the data set and uses all that we know about visualizations to come up with an initial representation of the data. And then we then give that to an LLM that does some sort of enrichment. And so, for example, the dataset description is generated by the LLM. So it looks at that initial representation, comes up with a description of the dataset. Things like the name of the file is done by the LLM. Things like semantic types. And so it's not just enough for us to know that something is a number. We want to know if it's a date. It's not enough for us to know if it's a string. We want to know if it's a location or a country, things like that. So the LLM will excel quite well at generating semantic types and also descriptions of each of the fields. Ideally, the next thing is, because we have this rich representation of our data set, it's not that long, but it sort of mirrors the amount of information an actual analyst would need to make good decisions on how to explore this data. We then give that to the goal exploration module that comes up with a set of, in this case, 7 questions that make sense for the visualization. In this case, it says the first one, what is the overall trend of the S&P 500 over time? And then it's a 3-part task. So for each goal, it comes up with a question. It comes up with a visualization, which is what we see in green. So here it says line chart of S&P 500 index over time. And then it comes up with a rationale, like what we might learn from this chart. And so it turns out that if you ask the model to generate these 3 things, you overall get ideas or exploration directions that are more meaningful. Next, the user could either select any of these goals, or they could come ahead and describe a goal that they're interested in, and then they could click generate. But the idea is that the visualization generation module takes in a summary and a goal, and then it can come up with charts that look like this. And so in this case, it came up with an original line chart, and then I gave an initial instruction and said, convert this to bar charts. I also said, translate the chart to Spanish. And so if you look at it, it actually has translated the chart title and axis to Spanish. And it has converted the original line chart to a bar chart. And it also has like an average price. The other thing you could do with LIDA is to ask the system to explain what this chart sort of does. And the first part of the explanation is an accessibility description, and we can take a look at that. So in this case, it has described, so essentially this part sort of describes the physical appearance of the chart. And so it says the chart is a bar plot with blue bars representing the price of the S&P 500 over time. The x-axis is this. It says the chart title is this, which translates to this in English, and it also describes the axis and also offers translations for them. And then it walks through the code. So for example, it says like there are several sections in code. This part just does import, library import. This section does data processing. So the date column is converted to a format. And then the third part does visualization, and it does explain what the code actually does. A value of this is that in many cases, when we put a tool like this in front of novice users, sometimes it might be hard for them to figure out if the chart is actually correct. And so as the chart gets more complicated, that becomes harder for novice users to validate or verify. And this sort of step-by-step explanation of what the code is doing, typically we're seeing users do things like, okay, that's not quite right. And then they can come back here using chart refinement and sort of describe all the modifications that they want to have made to the chart. The third piece here is evaluate. So here, essentially what we will be doing is we will give, because our representation is code, we give the code that's been generated so far, a description of the user goal. And then we ask the LLM to evaluate this chart across multiple dimensions here. So here we sort of bake in some visualization expertise. So we know that like things like chart type selection are an important dimension. We know that things like selecting the right encoding, selecting the right transformation are all dimensions that a good chart should actually address. And so we come up with 6 dimensions, and we ask the LLM to sort of self-evaluate this code and this chart that it has generated. And assuming it doesn't take too long, we kind of see the result here. So here, it sort of says on the, so there are 6 dimensions. So the first is bugs. So we ask the model, the system to evaluate if there are any logic errors in the code. It says here that the date column is converted using CRS, and there might be some side effects with that. So it says it might result in missing values. It says here that like, hey, the chart returns a matplotlib visualization, but the goal says that we want to see one visualization. So, and then finally, the title of the plot is Spanish, which might not be appropriate for the intended audience. So these are just ways, examples of ways that like we can leverage some of the language modeling capabilities of LLMs in doing things like visualization critique. The other thing that we see here is it says that the visualization is a bar plot, which may not be the most appropriate for showing the overall trend of the S&P. And here it says a line plot is more appropriate, right? And that makes sense. And also here, says, okay, compliance means does the visualization meet the goal specified by the user? And so it says, okay, yes, it meets that goal and all of that. And also reads it well in terms of aesthetics. But there are these 2 issues, so type of bugs. And so we can actually tell it, okay, now you've discovered all these errors. Can you go ahead and actually fix them? And it will actually take all of the critique it's generated, take the current version of the code, and then with the right prompting, it will apply that critique to the code, generate some new code, and then create a new set of visualizations. This might take a bit of time. So in interest of time, I'll skip. We might come back and take a look at these, but I'll skip back to the presentation. Okay, so I just walked through a lot of things, but let's sort of deep dive a little bit and sort of talk through how a system like LIDA works. And so LIDA has 4 high-level modules. So the first is a summarizer. So like I mentioned in the demonstration, you drag in your data set, the summarizer takes that in, it does the first pass using heuristics, comes up with a data structure that first summarizes the main ideas and summarizes the data set. And so it does things like predicts atomic type, generates a set of samples from the data set, computes things like the mean and the max, standard deviation where appropriate. And then it gives this representation to an LLM, which then enriches this on multiple dimensions. For example, it might predict a description for the entire data set, descriptions for all the fields, and semantic type. Next, that goes into a goal explorer. And so now we say, take the persona of a data analyst and come up with potential visualization ideas that make sense for this data. And then finally, each of these goals might be then put into a VIZGENERATOR module. So in this case, what's actually happening is we tell the system, here's a user goal, here's a representation of the data set, which a summary, write code that addresses this goal. And once we do that, we then have like a set of pre-processing and post-processing logic that extracts this code, refines it, fixes bugs, executes it, and as needed, we might apply some repair strategies and just to ensure we always give the user back a visualization. And then finally, we can take this visualization raster image that's been provided, and we can give it to an image generation model like DALL-E or Stable Diffusion or Latent Diffusion. And then by applying the right style tags, we can get like data grounded infographics. And so the idea here is that here we have like these bar charts that look like skyscrapers, but it still follows the overall structure of the data. Okay, so let's sort of walk through some of these modules. So the first is a summarizer. The task is to come up with an information-dense but compact natural language summary given the data set. 2-stage, we use a rule-based approach. We extract a base representation, and then we give it to an LLM, or a human can actually embellish or enrich these representation, like add descriptions and field names. And then we pass on that representation to subsequent modules. So what does prompt engineering look like for a module like this? And here, this is, I call this guy Squirrel the prompt writer. So you might see him a couple more times. And so the prompt might look like this. It says you are an experienced data analyst and you can annotate data sets, and you are to use the following instructions. You always generate a name for the data set and a data set description. You always generate a field description. You always generate a semantic type, and you sort of key that as a single word. And for each field and given its values. And so, for example, a semantic type might be things like company, city, number, supplier, location, gender. And all of this sort of prompts sort of come from a few experimentation. So just experiment with a few different things. But this is what the prompt for a summarizer might look like, or part of the prompts. And then we can ingest all of that data. So it's a JSON data structure, and we can sort of visualize that in an interface. Next, the goal explorer, and the idea is that it generates data exploration goals, and I like to call this EDA for free. And so the first step in any sort of data science or data analysis task is to come up with like exploratory data analysis, and a system like LIDA paired with LLMs actually work really well there. And so the one thing to note here is that we express it as a multitask generation problem. So rather than just saying come up with a visualization, we ask it to come up with a question, a hypothesis, a visualization, and also a rationale. And so it's like, what is the question? What is the visualization that will answer this question? And what might we learn from this visualization? And it turns out that if we structure the problem this way, we get more meaningful goals as opposed to just repetitive, heuristic sounding kind of goals. Again, what the prompt might look like is you're an experienced data analyst as well as a visualization specialist. You can read dataset properties and generate insightful questions about data. And in this case, we definitely want JSON, and so we give it some few short examples of what the result might be. And then we can then apply checks. So try to parse this result into JSON, and then figure out ways to sort of recover and repair in the event of errors. Next is the VIZGENERATOR. The idea is that it takes in a goal, takes in a summary, and generates visualizations based on a code scaffold. And so the idea of a code scaffold is that it's a template. And so an example template is what we see on the right. All of the imports, the model is giving some sample imports, is given a structure for the plot function. That structure is sort of empty. And as opposed to just telling the model, generate code that meets this goal based on this data, we instead convert that to a fill in the middle sort of task where we say, here's this template, here's this goal, here's the summary. Now extend this template to fit the goal. And it turns out that if you can guide the generation process using the template, then the reliability of you can improve the reliability of the overall system. So for example, if you don't provide the structure, the model might make all these assumptions about some data being available, fonts being available, some additional files being available. It might make assumptions on the structure of the code. It might attempt to import libraries or functions that don't exist. And so, and all of this can drastically interfere with the reliability of the system, especially if you're using a less capable model. So GPT 3.5 might make mistakes like that. GPT 4 is less likely to make mistakes like that. But overall, you want this sort of structure such that you can also do some good post-processing at the end of the day too. An example of what the prompt looks like is your helpful assistant skilled in writing visualization code. Of course, you need to tell it you need to follow visualization best practices. For example, if you remove things like this, the model might occasionally generate a pie chart. And in the visualization community, you sort of, it's like a best practice to avoid using pie charts, mostly because it can be hard to compare the quantity of each values in a pie. And the recommended thing is to use bar charts instead. And so if you add like instructions like this, then the model is less likely to just generate pie charts. And then also we sort of instructed to use the provided code templates and just don't add extraneous material. And this overall improves the reliability of the system. Next is the infographer. It's a smaller part of this project, not extremely well developed at the moment, but the idea is that like whatever comes out from the Viz generator or from whatever visualization refining process we apply, we can take that. So the output of that process is a raster image. And we can take that raster image and we can give it to a latent diffusion model and do some text-based conditioning. In this case, we say we use underwater art, seashells, and the key point here is to control the diffusion parameters such that the output image is strictly conditioned on the input image. And so the reason is because we want the overall structure of the input image to be maintained such that like this generated infographic is still meaningful in some way. Okay, and these are some other examples. Here we have like an actual chart of precipitation, and then we say, generate an infographics using tags like raindrops or leaves or underwater art, seaweed, and all that. And there's a lot of applications for this in, for example, things like data story generation. So imagine that you have like a system that takes in data and could generate stories paired with visuals. So data grounded or data faithful visual artifacts. So at the end of this first process, we have the Viz generator that has generated this visualization that is code and also an image. So there's a code representation, there's an image representation. In theory, we can apply a bunch of operations on this code representation. And so in the demo, I hinted at like how you could ask questions of a generated visualization. So things like change the axis to X or Y, translate the title to Spanish or I don't know, any language. And essentially, these LLMs pretty much are good at free-form language translation. You could tell things like take the trend line, drop it by 300 points, and plot a new trend line. You could say things like add a regression line that is a regression between X and Y parameters, and the model is quite good at handling things like that. The other piece which I showed in the demo is explanations and accessibility. And so this is super useful for building systems that individuals with vision impairment can sort of interact with. It's a very, very important part of visualizations because typically visualizations have been out of the reach of users with vision impairments. But with systems like this, in addition to generating the visualizations, you can generate accessibility descriptions. At least to sort of describe the physical appearance of the chart. And then also to enable debugging, you could provide this sort of natural language explanation such that novice users can sort of make sense of what the code does and use that as a framework to sort of improve or address bugs. Then next, self-evaluation, critique, and repair. So we sort of looked at the example where the model discovered that a bar chart might not be the most appropriate type for an S&P 500 type of line chart, and sort of use that to, and then use that feedback or self-critique to sort of auto-repair itself. Then finally, visualization recommendation. So as you interact with the system for each request you make, you could typically ask the model to come up with additional visualizations that might make sense given the current representation. So I categorize all of these as VizOps because the idea is applying operations on the code representation that we might have had obtained from a previous process. Okay, I will breeze through some related work. So the first is foundational models for creative tasks. And so I'm sure we're all familiar with foundational models. They're trained on vast amounts of data across multiple modalities. They can encode the semantics of the data distribution really, really well. And they've been applied to a lot of creativity related tasks, such as writing, coding, image generation, music generation. And LIDA just leverages those models out of the box without any change. And so in this case, we use GPT 3.5 and GPT 4, and we use that to sort of take advantage of its code writing and language modeling capabilities across different modules in LIDA. Another set of relative works has to do with like automated visualization generation or visualization recommendation. And we can sort of categorize them into three high-level areas. And so, for example, rule-based approaches that looks at, there are a bunch of rules. We extract properties of data sets, and then we try to match that with some of these rules and figure out visualizations that might make sense. Another set of work sort of looks at task decomposition. So, for example, there's been some work on natural language to visualization. And sort of they build independent modules to do things like query generation, query disambiguation, and come up with like custom domain-specific languages for visualizations. There are some limitations to that approach. Then there's end-to-end learning approach, which is the closest to what's done here in LIDA. And the idea is it's by using LLMs in LIDA, we sort of figure out a way to take advantage of the broad world knowledge. So it turns out that these models have learned visualization best practices and sort of leverage that in chart generation. And then finally, infographics, there's a bunch of work on creating pictographs. LIDA sort of extends this using latent diffusion models to create data faithful infographics. Okay, system evaluation. The process of evaluating a system like this can be tricky. So for three high-level reasons. So the first is LLMs are stochastic. Ideally, if you want to put this in front of the user, you want to create a pipeline that is at least on the minimum bug-free. What that means is that like you always give the user a visualization that is valid. Now, the quality of the visualization, that might vary, but on the minimum, you want to make sure the LLM hasn't generated bad code that gets executed, hasn't generated bad JSON. You want to figure out a way to sort of defend against that, or at least measure how often that happens. The second thing is beyond system reliability, there's also the issue of visualization quality and how might you sort of start to address that. And then third is the issue of memorization. So LLMs have seen a significant chunk of all the data that's available. And so, for example, there's always the argument that when your LLM does well, does it do well because it has sort of reasoned through the current task, the properties of the task, or it has merely just remembered or regurgitated something it saw during training. And this is a really tricky, thorny problem. And the one approach is to just construct new tests, benchmarks, or much more different or recent data sets, and then sort of use that to study model behavior. So currently, LIDA sort of looks at this problem from two main metrics. The first is visualization error rates. Is the percentage of generated visualizations that result in compilation errors. And so in this case, we took about, we generated about 2,200 visualizations using datasets sampled from the Vega datasets repo. And for each dataset, we asked the LIDA to come up with 5 goals. And for each of those 5 goals, we asked it to generate visualizations in 2 grammars, so Matplotlib and Seaborn. And we give it only a single shot, a single chance for each of these tasks. And so the chart here just is a representation of an ablation study. So when we use, so this is based on the summary. So when we use no enrichment, and so we don't add like semantic types and all of that. For this data set, we see that like error rate is about 3.86. And so if we look at just seaborn, when we enrich the data set, that's we add semantic types and dataset descriptions. It provides a bit more information, and for seaborn, we get a slightly lower error rate. And then in the case where we just provide only the schema, which is something that a lot of existing LLM-based approaches use, to just tell the model, oh, here's a list of the fields or in the data set. And it turns out that error rate is almost 3 times as much because the system just doesn't have enough context. And then if we don't provide summary at all, a summary of the field names, and if we don't provide each of the columns that are available, maybe we just provide only the file name, then error rates are very, very high. And one other thing to notice is that overall, seaborn the system seems to do better with seaborn compared to matplotlib. And my explanation is that seaborn is just a much more expressive visualization grammar, and even across other visualization grammars, seaborn still seems to be the give the least visualization error rates. The other way we measure visualization quality is to use GPT-4 to sort of score visualizations across 6 dimensions. And GPT-4 is very, very good at this task, at least compared to GPT 3.5. And then we can compute this over the entire data set. This is just an example. One other, so I have this slide just as an example of, it's not extremely rigorous, but a question that that always comes up is, do models like GPT-4 encode visualization best practices? And if you just went to, let's say, the interface in OpenAI.com and you ask a question like list 10 visualization best practices when writing code to generate visualization and charts, and the model actually generates a lot of really, really sensible things. And essentially, as you start to use the same model to critique visualizations represented as code, you actually can see that a lot of this knowledge actually translates to the sort of critiques that the model sort of enables or advocates for. And so I have a website where you could go look at the galleries or examples of just for qualitative inspection of what the model output sort of looks like. Okay, so I will conclude now. I think I'm right at the 45-ish minute mark. Some lessons. So the first thing is a system like this needs to be fast. For that, all of the calls for each of the models is structured as a single call. So for example, summarization and enrichment is a single call to an LLM. Goal generation is a single call, even though for each goal, the model does 3 things, but it's all structured as a single call. The second important thing is the use of code scaffolds, so prompt scaffolds. So just do not ask the model to generate visualizations or generate anything freeform. The prompt is your opportunity to bake in domain expertise and bake in your knowledge of the problem space. And in this case, it sort of like improves reliability. The third thing is, in many cases, you require the model to return a structured output format, so for example, JSON. And the reason why you want to do that is you can use that as a way to sort of detect errors and implement error recovery mechanisms. And then finally, prompting has an outsized effect on performance. And so this project is kind of old. So it was started in August last year, and we were I was using DaVinci 3 as an earlier version of GPT-3 from OpenAI. And the error rates were as high as like 30%. Then we switched to ChatGPT came along and switched to ChatGPT, which is GPT 3.5 Turbo, and error rates sort of went down to about 50%. And then just from carefully improving the prompt scaffold and the pre-processing and post-processing, we have error rates of about 3.5%. And even in that domain, you can use automatic repair, self-repair, self-critique, and repair to sort of drive that down to 0. So what are limitations, or second to last limitations of this approach? It works well for data sets or grammars that are represented in the training set. And so, for example, tools like Power BI or Excel that are primarily graphic based, and so they're not specified in code. Or maybe other visualization grammars that are, let's say, very niche. The system might not perform very well there without some additional fine tuning. The other thing is that there's a trade-off between how flexible the system can be compared to how much leeway you give it in the code scaffold. And so it's there's a bit of a tension or trade-off there. And then also this system executes code. And so what it means is that you need to run it in a sandbox environment just to be safe. In terms of next steps, there's work to extend the benchmark, include tests, more rigorous tests on how well these LLMs encode visualization best practices and how they transfer to self-critique and self-evaluation. There's opportunities to improve the library itself, applications and data cleaning, optimizing for latency, and then just high-level data story generation capabilities. And at this point, I'd like to end. Thanks a lot for listening, and I'd love to take questions now. I don't see any questions in the chat.
Yeah, thank you very much. There is no questions in the chat so far, but I know people will be able to ask questions. Thank you. It's a wonderful talk. I don't know. We're actually shooting behind time now, and it's to keep it short. Let's call for questions. So have one from Paul. Paul, you can unmute yourself.
Thanks very much, Victor. That was really interesting. A very nice piece of work. I think it's accepted for ACL demo, is it?
Yes, that is correct.
You'll be presenting that as well. It's really interesting. I guess one question is whether you can turn it the other way around and use it in a way to write the question and the system goes to find the data. So at the moment, it sounded like the start point is you start with your CSV, you drop it into the system. But could I write a question and say, I don't know, summarize the air quality in the center of Lancaster City over the last 10 years?
Yeah.
And it goes and finds the data, or it might, and presumably then there's some, checking for how complete or how much data is available publicly, but whatever you can get, you can drop in and then run the system that way.
Yeah, that's a great idea. There's a lot of work ongoing around like autonomous agents. And so the idea autonomous agents enabled by LLMs. And the goal is to sort of figure out a way to enable LLMs sort of act in the real world on behalf of the user. An example of an action will be a search action or a data search or data discovery action. And so typically what you want is like an LLM that sort of is, the system is well optimized to, let's say, use a search engine, or maybe also use some internal search system, sort of inspect all the results it gets, extract links to CSVs, parses them for quality, and then makes a good decision when it has found a couple of data sets. And then that system can be separate, and it might treat LIDA as a visualization engine and say, once I've done all this search, I've aggregated all this data, I have all this nice metadata. Then you can give that to LIDA and say, okay, visualize this. And this could be even more interesting because you could extract some of the context. Let's say you got the data set from a web page. And so now you know a bit more about it. So the summarization module doesn't need to work in the dark, trying to predict the dataset name, its purpose, or the columns. And so maybe you can merge that data with what the summarizer can do just to get much better performance. But the answer to the question is you need like a module on top of LIDA. And what that module would be is like an autonomous agent style kind of module.
Right. Yeah, brilliant.
Yeah.
Thank you very much.
Thank you. Is there any other question? While we wait for people to answer to ask their questions, or they're thinking about it, maybe. I guess my question will be, one of my questions anyway, will be from an NLP researcher point of view. So LIDA currently receives only structured data sets, right?
Yes.
Do you envisage a time, or do you is there any way unstructured data can actually be passed on that, leveraging the powers of LLMs today? Or do you suggest having another module on top of LIDA again that does that?
Yeah. So it depends, right? So assuming we want a visualization as part of the outcome of your system, then LIDA can be like part of it. So LIDA is optimized to sort of take in like tabular data sets. So this is just a regular understanding of tabular data sets, rows, columns with column descriptions, right? But let's assume that we want to start with unstructured data. Let's say we had like a play 12th night. So it's a whole play. And maybe what we want is to figure out a way to visualize the 12th night. And so we might then build this whole system that attempts to extract structures, to construct structured data from unstructured data. And I think the engineer has a lot of leeway on how something like this could be designed. So let's stick with the 12th night example. Imagine that we split it into chapters and acts. So let's say we say chapters. So now we have several columns. It says chapter 1, act 1. And then maybe for that, we can then tell the LLM to, let's say, count how many times each character spoke at all. And an LLM is pretty good at doing things like that. And so that way we can then create like a column where for every character, we have like a column for every character, and then we have a number under each of those characters. And so that way, imagine that we then gave that thing to LIDA. So LIDA will happily come up with a chart to say something like a chart of, I don't know, say characters speaking over time. And you will show that plot that says that maybe on the x-axis is act 1, scene 1, all of that. And on the y-axis is just a count, just maybe cumulative count of how much that person spoke. So that's just an example of how like we might like convert like unstructured, and models like GPT 3.5 and 4 are really good at this sort of they will do quite well at like faithfully counting say the amount of times a person spoke. But then there's a lot of engineering aspects to that too though. So
thank you very much. I guess that's also what the way I'm thinking. I know Paul will know where I'm going with this kind of question, because the nature of the data we're working on, it's like that. All right. I don't want to dominate this. It's almost 4 o'clock from here now. And by the way, thank you, Victor, for waking up so early to do this. From where you are. Is there any other question? I still have one more before time runs out. Any other question? Okay, I can't see any now. Just one more question, because we didn't quite start at 3 o'clock. Right now, you have tested this on, or rather you leveraged the OpenAI's GPT 3.5, 3.4. Yeah. How easy is it to also plug in other LLMs from other companies?
Yeah, so one thing I should mention is that like I'm in the process of making this tool open source. So if you do find it, you'll find the project page with some example galleries, but the code, I'm thinking maybe sometime in the next couple of weeks, ideally by ACL, it should be available. So that's one thing to note. But yes, the text generation core module has a wrapper for local models as well as OpenAI models. And so even like small LLMs like T5, you should be able to use that. Of course, the accuracy would just be less, but in theory, you really should be able to use any type of language LLM to sort of work with a tool like this. And what it might mean is that like once the system is open source, then we can do some work in implementing specific wrappers for things like, let's say, Anthropic. So there's no specific, like maybe we could, and that is kind of trivial. It's kind of simple to do, but yes.
Okay, thank you very, very much. All right. Thank you all for sticking around. I know that some people have other meetings to join. And this is recorded and will be on our YouTube channel soon. If you do have questions for Victor, I know his contacts are all on the advert that I gave. If you pass it through me too, I will pass it on to him. Victor, thank you very much for coming to give us this talk. We are stopping, not because we don't have more questions. We're stopping because time has actually gone. So
Yeah.
we will keep coming back to you with this.
All right. Well, thanks for having me.
Yeah.
Enjoy the rest of your day.
Yeah, bye. Thank you.
Bye.